everyone. Welcome if you're new and welcome back if you're not. My name is Talia and I'm an incoming fourth year student at UCSD studying chemistry. This YouTube channel is an extra resource for anyone who may need some help to boost their chemistry knowledge. In this video, I'm going to be wrapping up the unit on equilibrium basics by talking about manipulating equilibrium expressions. I hope that if you need some help with that topic, you will keep on watching. And without further ado, let's get started. All right, let's go ahead and get started with my slide deck on manipulating equilibrium expressions. So it's similar to when you're doing Hess's law and you're given different steps of a reaction and asked to put them together to get the overall reaction. The same thing can happen with different equilibria that make up a full equilibrium reaction. So there are two kinds of problems that I've put here. There might be different variations that I'm not thinking of, but these are the two main ones I've seen, is that you may be given a reaction, an equilibrium, and asked to turn it into a different reaction and figure out the K. Or you might be asked to put two equilibrium expressions together and figure out what the K is. The same rules apply to manipulating equilibrium expressions, regardless of what the problem is asking you to do. But I just wanted to show you two different forms of problems that you may see in your classes or in your homework. Okay, so there are two main rules. You can kind of divide this into three rules, but I feel like it's easier to just explain it in two. The rules are also different than when you're multiplying steps of a reaction in thermodynamics and trying to get the delta H. So if we multiply an equilibrium expression by a coefficient, for instance, multiply it by 2 or multiply it by 5, you raise the K to the power of that coefficient. The part that is sometimes separated from this rule, but is technically still the same rule, is if you flip a reaction. If you flip a reaction, it's the same thing as multiplying it by -1. And you might hear people say, okay, in that case, you're going to take the reciprocal of your K value. I like to minimize how many things I have to memorize, so I mush it into this first rule that if you multiply something by -1, if you multiply by the reaction by -1, you're going to raise the K to the -1st power, which is the same as doing the reciprocal. And I personally think this is really handy for when you need to do something like flip the reaction and multiply it by 2. It's, in my head, easier to just raise it to the -2nd power, then do the reciprocal and then square that. You can do whatever is easier for you or whatever is in line with what your teacher has been explaining, but I just wanted to provide that alternate option. Okay, the second rule that is different than Hess's law is when you add equilibrium expressions together, you multiply their K values. Okay, so now we're going to do this example, and I'm going to walk you through a couple strategies that you can use to solve this problem. So I have three different equilibrium expressions. I'm not going to read them all out, but the overall expression we're trying to get is 2N2O plus 3O2 is an equilibrium with 2 moles of dinitrogen tetroxide. Okay, and we're trying to get these three expressions to fit into this one. There are probably multiple different strategies you can do. I am going to show you my thought process. I like to first figure out which compound is only in one of the reaction steps. And that happens to be N2O4. So I'm going to highlight it. The N2O4 is right there. So I'm going to just focus on putting the N2O4 exactly where I need it to be and with the correct coefficient in front. So in the overall reaction, it has a 2. In the step that we're given, it has a 1, and it's on the reactant side. So what I'm going to do, I want to flip my reaction 2, let's call this 1, 2, 3, and also multiply it by 2. And that means, if we go along with the rules, that I'm going to raise the K to the -2nd power. You can also take the reciprocal of the squared value. Okay, so now I've taken care of that first one. I'm going to write it down here. And then we want to raise the K to the -2nd power. K is 47,259. Let's just say that. Keep the unrounded number in your calculator. Okay, now I've taken care of N2O4. Okay, now the next thing I'm going to do is try to find another reactant or product that is in only one reaction step. I'm going to highlight it in a different color. I see N2O. So now I'm going to put that exactly where I want it. And we see that the N2O we're given in the mechanism has a 2 as a coefficient and it's a product. But in the full reaction, there's a 2 and it's a reactant. So I'm going to flip reaction 1 and not multiply it by anything. I'm going to raise the K to the negative first power or just take the reciprocal. So that's going to be 1.2 times 10 to the negative 35th to the negative first power. And K is going to be 8.33 times 10 to the 34th. If we wanted to worry about the sig figs a little bit more, we could make the K for reaction 2 47,000, or write something in scientific notation. Okay, last one. This one, now we have O2, which is in the first and the third reaction, so we can use that. Or we can try to get rid of the N2s and figure out, because there's no N2s in the final reaction, but we have N2 in reaction 1 and reaction 3. So this is where the paths you can take kind of diverge. So in reaction 1, I've manipulated it now that we have 2 N2 moles as a product, which means I need to have in one of the steps 2 moles of nitrogen gas as a reactant so that they cancel out. And the way we're going to get that is by multiplying the whole reaction by 4, which will multiply the 1/2 by 4 to get 2. Another way you can go about this is that you want 4 moles of oxygen gas. We see that we've manipulated reaction 1 so that there's 1 O2 as a product, which means we need to have 4 O2s as a reactant so that when we simplify, there are 3 moles left as reactants. Now I'm going to rewrite reaction 3. That means we're going to raise our K to the 4th power. So we're going to do 4.1 times 10 to the negative 9th to the 4th, which is going to be, let's just say, K equals 2.8 times 10 to the negative 34th. Okay, now we're going to put all these reactions together. In this part, we're just going to sum them up and cancel out things that are the same on both sides. All right, so I'm going to start. We have our 2N2O. So let's just look for similarities. We have 2 N2s on both sides. We have 1 O2 as a product and 4 as reactants. So the one on the products is going to go away, and we're going to be left with 3 as a reactant. We also have 4 NO2s on both sides. Oh, that's another pathway you could have gone down for reaction 3. So now I'm going to write our new reaction, and spoiler alert, it is going to match the reaction that we have. Okay, there's our reaction. So we've done step 1, or I guess like the second part. Now we need to calculate K, and I'm going to multiply the 3 values together using the unrounded numbers in my calculator. So the 40th at 7,258 times the 8.33 times 10 to the 34th times the 2.8 times 10 to the negative 34th. And you're going to get 1,112,854, but we're using 2 sig figs, so I'm going to round that to be 1.1 times 10 to the 6th. And that is all for this problem. That is one kind of equilibrium manipulation you will see. And I think these problems are really fun because you're kind of solving a puzzle with these equations and trying to get to your desired reaction. That wraps up this video on manipulating equilibria, and it wraps up the unit on equilibrium basics. Next time, I'm going to start talking about solubility equilibria. So if you need some help with that, feel free to join back next time. If you have any questions or comments, feel free to leave them in the comment section below, and I will do my best to answer them. I hope you learned something new from this video, and good luck with learning chemistry.